Hello everyone, I'm Salma Sanchez and in this video, I'll be explaining the cell lysis step in a downstream processing scheme, more precisely by agitation bead milling and high-pressure homogenization. This will be the content of the video and we're going to start with a little bit of history. Modern high-speed agitator bead mills have been developed from the ball mill, which is reported to have been used for grinding flint for pottery in 1870. This ball mill was a hollow cylinder rotating at low speed around the horizontal axis. In this mill, the speed of rotation was limited, because with increasing speed of the cylinder, the resulting centrifugal forces eliminated the cutting effect. To overcome these problems, a new type of mill was constructed in 1928, in which a slow-running agitator was used to keep the ball charge moving. About 20 years later, because of the increasing demand to produce materials with very small particle sizes, the first vertical mill with a high-speed agitator was introduced. In the following years, improvements of the agitator design and media separator were carried out. In addition, horizontally mounted grinding chambers became available, where the gravity as a grinding factor was minimized. Bead mill as a cell disruptor technology in the laboratory was pioneered by Tim Hopkins and originally commercialized by Biospect Products in the late 1970s. In the last decade, products processed in agitated bead mills are growing fast. Depending on the process, vertical as well as horizontal high-speed agitator bead mills are used today, and special agitators are designed to improve the comminution and to produce a uniform acceleration of the beads, resulting in products with narrower particle size. Now, for the high-pressure homogenization history, the first version of what should later evolve into this technology was invented by the French engineer Auguste Gaulin in the early 19s. It was originally constructed for increasing the product stability of milk by reducing the fat globule size and thus the rate of cream separation. In 1961, stainless steel-clad frames are introduced and quickly become the norm for food production environments. In the whole 60s decade, the use of homogenizers spreads beyond the dairy industry to include chemical, lubricants, textiles, and many others. Then, in the 90s, the biopharmaceutical industry begins to require homogenizing pressures of 10,000 psi and beyond, pushing further technological development that was accomplished in the next years with the Gaulin and Rani brands. From 2010 to present, further changes have been made to the power frame design to improve access for maintenance and ease of use. Now, before discussing each technology's principle, let's define cell lysis. Cell lysis is an additional step in downstream processing used to break open the host cells, allowing the liberation of intracellularly produced target biomolecules. Here we have a downstream processing scheme for the purification of intracellular recombinant therapeutic proteins from microorganisms. As we can see, the cell lysis step for product release has a direct impact on the whole bioprocess, which is why it's essential to define the criteria for an optimal cell disruption process. The available techniques to do so are broadly categorized into mechanical and non-mechanical methods, which then include physical, chemical, and biological techniques. In mechanical lysis, cell membrane is physically broken down by using shear force. These methods are the most popular for large-scale purposes because of a combination of high throughput and higher lysing efficiency. The destruction of cell membranes and walls by these methods is effected by subjecting the cells to shearing by liquid flow, exploding by pressure differences between inside and outside of cell, or to collision forces by impact of beads or paddles. Now, agitation bead milling technique involves the use of beads which are placed in a jacketed high-speed reaction vessel. In this class of agitated bead mills, the beads and the cell suspension are loaded into a chamber. Into the mix is placed one or more spinning discs that accelerate the beads. And finally, the beads striking the cells combine with the shearing by the moving liquid phase to disrupt the cells, as we can see here in the animation. For the comminution of added solids, the agitator has to transfer kinetic energy to the beads. This energy transfer is accomplished by adhesion forces in combination with displacement forces. Both are related to the geometrical design as well as surface and material properties of the agitator. The beads are accelerated in a radial direction, forming stream layers of different velocity and thus creating high shear forces. The differential velocity between the layers is influenced by the size and density of the beads, and the distance to fixed or rotating parts in the grinding chamber. The energy of the grinding elements is maximal at the periphery of the agitator disc, while it is minimal at the chamber wall and near the axis. Another factor of disruption, although at a much lower level, is the frequency and strength of collision events between the beads. The kinetic energy of the beads can be maximized by increasing the peripheral speed of the agitator discs, which is the reason why high-speed agitator mills are used nowadays. Now, in high-pressure homogenizers, the liquid stream of suspended cells is forced at high pressure down a narrow channel or across the small gap of a valve. This accelerates its speed, thereby stretching and shearing cells. In some designs, the moving stream is subsequently and abruptly impacted against an obstacle to further damage the cell's membrane. A model has been proposed to relate the amount of protein released by homogenizer to the applied pressure for E. coli, where R is protein released, Rm is the maximum protein available for release, P is pressure in millipascals, N is the number of passes, and K is the rate constant, and A is the pressure exponent. Since the release of protein is independent of biomass concentration, higher concentration of cell can be disrupted at the same time. However, generation of heat is a problem in this method. Cooling systems can be used to minimize the heat generated. In high-pressure homogenization, there are two versions of impact. The first one, the stream is directed to slam against an impingement wall. This homogenizer consists of a high-pressure positive displacement pump coupled to an adjustable valve. By adjusting the gap or clearance in the homogenizing valve, the flow area is controlled. When the flow area is increased, the pressure is reduced. When the flow area is reduced, pressure within the pump discharge manifold increases. This high pressure generated by the pump is converted to fluid velocity and heat. In the second type of impact, the stream is split into two legs of a Y, and these lines are then directed at one another in an interaction chamber where they collide, further disrupting the cells. The media that contains the cells is forced through the narrow channels of the proprietary interaction chamber of the processor. Inside these channels, with typical dimensions of 75 to 300 micrometers, the fluid achieves velocities up to 400 meters per second. High pressures, up to 275 millipascals, are required to generate the high velocities inside the interaction chamber. Studies of the disruption process in homogenizers have shown that the primary mechanism contributing to disruption is impingement of a high-velocity jet of suspended cells on a stationary surface. The cell suspension accelerates to a very high velocity as it passes between the valve and valve seat and then impinges on the impact ring. Other types of stresses generated by the homogenizing valve include shear stress and normal stress. Although neither appears to be effective in causing disruption of microbial cells, there may be some enhancement of the disruption process by turbulence in the fluid. In the last decade, products processed in agitation bead milling are growing fast and applications cover a broad region. For instance, in the printing industry for the production of inks, dyes, and coatings. Same for producing primer coatings, lacquer, and pigmented dispersions. It is also applied for the metal oxides for tapes and discs. Also, for the ferrites and high-grade ceramics in electronics. For mineral slurries in water or oil, and finally for chocolates, food dyes, peanuts, and other food industry products. High-pressure homogenization also has many different applications besides cell disruption. It is widely used to create stable macro or nano emulsions and dispersions in industries like food or pharmaceutical, to prevent creaming and coalescence, to reduce particle size, and to mix ingredients. In the pharmaceutical, cosmetics, and biochemical industries, it can be a tool for handling solid lipid nanoparticles and crystalline solids, drug nanoparticles, and nanosuspensions. Finally, microbial inactivation is one major application. It can induce a reduction of the microbial load of food products to the level of pasteurization and even sterilization, depending on processes parameters. There are many different models and manufacturers for both technologies. For agitation bead milling, there are laboratory mills with working volumes of 50 milliliters up to 2.5 liters, and these are offered in continuous and batch operation. For pilot plant operation, it is customary to use mills with grinding chambers in the range of 5 to 25 liters, while for production purposes up to 250-liter chambers are commonly employed. For special cases, 500 and 1,000-liter mills have been built. For high-pressure homogenizing, there are lab-scale models processing minimum 14 milliliter sample volume, as well as pilot-scale models with a capacity of 1.2 liters per minute and maximum pressure of 105 millipascals currently available. Production-scale models have a higher maximum pressure of 70 millipascals and are capable of processing up to 15.6 liters per minute. Here's a table enlisting the most common trade names for both technologies, as well as their responsible companies and websites. For high-pressure homogenizing, SPX Flow, which is selling the APV Golan model, has the greatest popularity in the market, together with microfluidizer. For agitation bead milling, the DynoMill product is one of the most sold by WAP Group. Speaking of versatility, these two techniques are useful to release products of interest that are located in different parts of the cell, such as the cytoplasm, bound to the membrane or cell wall, in the periplasm, and also in inclusion bodies, which are particles of aggregated proteins. In this last case, the inclusion bodies must be isolated, the recombinant protein of interest resolubilized, and in most cases, refolded into its native structure. Inclusion body yields do not vary significantly between high-pressure homogenization and bead milling agitation, but the physical characteristics of the homogenate do vary, including the viscosity and the cell debris size distribution. Also, the beads of a bead mill can still be separated easily from inclusion bodies by sieving, because the beads ranging from 0.5 to 1.5 millimeters in diameter are an order of magnitude larger than inclusion bodies. There are many other alternative techniques to perform cell lysis, but at the large-scale level, the number of choices is clearly reduced. One option could be ultrasonic shear by collapsing bubbles. Here, the use of sound waves in fluids is used to disrupt cells. The operation starts with normal electrical current, around 60 Hz, being transformed to 20,000 Hz. This electrical signal is fed to a piezoelectric crystal, causing it to oscillate at this high frequency. The vibrations move a titanium metal horn in the fluid, moving the liquid forward and retracting quicker than the liquid can return. At this point, the pressure in the system drops below the vapor pressure of the liquid, so boiling occurs, as cavitation. As the liquid flows back, the bubbles collapse, which imparts the energy needed to disrupt the cells. Another alternative is rotor-stator homogenizer. This consists of a rapidly spinning paddle contained within an open-ended tube with slots near the working end. The turning paddle pushes liquid out the slots, creating a low-pressure region that draws suspension up from the open end. As the sample is pulled up, there is a stretching action. Then, as the material is forced between the narrow gaps, there is a cutting action. Finally, regarding advantages and disadvantages, with this image, we compare selectivity of product release and the ease of product recovery, and we can see some advantages and limitations of both techniques. As we've already seen, both can efficiently process large volumes of liquid sampled thoroughly and reproducibly. However, the product release is not selective, which involves the presence of contaminant cell debris that brings downstream complications and costs. Moreover, both methods have been shown to be effective against rigid cells, but unfortunately, they also involve a significant heat reduction, which leads to damage by denaturation of the product of interest. For this reason, it's essential that these technologies provide a rapid chilling of the effluent, or an active cooling of the apparatus, as seen as one of the advantages for bead milling. I hope you found this video useful. Thank you for your attention.